Okay, so this was the frame we didn't get to during class, and we're going to get it finished today. And remember, we've been talking a lot about two force members, and what we need to remember about two force members is they literally only have forces at the ends, and they can look like an angle. I mean, we saw that. Oh, that's not right. I need to erase that. We saw that if we have a two force member, then the vector has to act between the two ends. We could have a curved member. And again, that vector has to act through. So we know the direction that the resultant vector for the x and y components are going to be happening. And that's what one of the beauties of a two force member is it takes some of the guesswork out. How are the x and y reactions related? This looks an awful lot like a two force member, but this is not, okay, not a two force member. Okay, it is in fact a three force member. 1, 2, 3. So when I look at the reactions here at the end at C, I can't just say that the resultant is acting through the center of my member. Therefore, the x and y components have to be at sine 60 and cosine 60, because this is not a two force member. So we cannot use this rule. We cannot use that rule. Two force member, literally only two forces. Once you put another force on it, it's now a three force member. Okay, so we have two three force members that are making up this frame, and I can see at A, I have a pin, and I know with pins it can resist translation up and translation sideways. And I have another pin, which again, I can resist translation up and translation sideways. I could rotate. Okay, a pin is like, think of a door hinge. So I have 1, 2, 3, 4, and I don't have the luxury this time of being able to break these two components as a relationship of sine 60, cosine 60 of that compression member, because it has that added moment. It's going to change that relationship, okay? But I do notice I have an internal pin, or a hinge, whatever you want to call it, internal pin. And so I have 4 unknowns. I have 3 equations of equilibrium. So that gives me one unknown. And I can cancel that out because I have that internal pin, minus 1. So we are back to, we can solve this problem. We're going to have to use equilibrium and take it apart at the pin. So it's like I've unscrewed it on my workbench, and I've laid AB out, and I've laid BC out. So we are going to just start with this time. Sometimes I start with the overall, sometimes I start with, one of the sections. If I look at section BC, and I know that there's a pin that's got the X and Y components, and C has X and Y components. I don't know the ratio of the X and Y components here or here. It has too many unknowns. If I sum the moments about point B, I'll have an unknown CX and CY. If I sum the moments about C, I'll have an unknown BX and BY. I'm back to 4 unknowns, and I don't have enough equations. But because I have this straight member right here, it kind of gets rid of all of my X unknowns, and it leaves me with the ability to sum moments and calculate something that's going on. So let's start with free body diagram of AB. And remember, always label what it is you're doing so that we know what it is you're doing and you know what you're doing. And I'm going to have AX, AY, and I'm going to have BX and BY. And I don't know which direction they're really going, but they have to have both X and Y components. Okay, and I could have a free body diagram of BC. And it's coming down like this. And so I'm going to have BX going back to the left and BY coming up. And then I have CY and CX. And again, I'm just assuming a direction. I don't really know which way they're going. This one has an applied moment of 750 pound-feet. And we have a point load over here of 150 pounds, 3 feet, 3 feet. And I know that this is 60 degrees, and here we go. My hypotenuse is 4 feet. Okay, so if I look at a triangle, sine is opposite over hypotenuse. So I have sine 60 equals, we're going to call that y, over 4 feet. So y equals 60 sine 4 times. So I have 3.464 feet. And this is sometimes where you have to put on your thinking cap. You have to put on your thinking noggin, because we're not going to necessarily give you every single vertical or horizontal direction you need. You're going to have to go back and think about, what do I know and how can I get there? And I do know this is a right triangle at 60 degrees, and I do know the hypotenuse. So I can use trig to come back and calculate the side length. So I have cosine 60 equals x over 4 feet. So this bottom part of the triangle, x cosine 4 times, it equals 2 feet. So if I wanted to go back up to this picture, okay, and just kind of label on here, I know that this distance is 2 feet over. So from A to C, it's 3 plus 3 plus 2. And I also know that this height then, from A down to C, is 3.464 feet. Okay, so that's my overall geometry. So I have these two pictures, and clearly if I sum moments about C, I've got a BX and BY. Because this isn't a two-force member, I don't know how they're related to each other. So I'm going to start up here. So let's start with, let's sum our moments about B. They should equal 0. And if I'm summing my moments about B, I'm going to stick my finger here. I could even make a little clock hand. I'm going to push up at AY. Oh, that does cause rotation about B. So I have negative AY times 6 feet. Okay. Here's my clock handle, pushing down. Oh, it indeed causes rotation. Plus 150 pounds times 3 feet equals, well, this goes straight through, 0. So I have 6 AY equals 450 pound-feet. AY equals, get my calculator out, 450 divided by 6, and I get 75 pounds. I assumed up, I got positive, it is indeed going up. So I can put 75 pounds here. Erase that out. And I know if this is 75 pounds, I have a force here, I could actually find what BY is. So I can sum forces in the Y direction equals 0. Okay, and I have AY minus 150 pounds minus BY equals 0. I have 75 pounds minus 150 pounds. I'm going to make that a positive, equals BY. So BY equals negative 75 pounds. Now what that means is I assumed that BY was going down, and it is really going up. So if it's going up here, then it has to be going down on this side. So I was wrong. It goes up. Okay? Now, I cannot just say I'm going to sum the forces in the x direction, therefore AX and BX are 0. That's not true. All that I'm going to know if I sum forces in the x direction, that AX plus BX equals 0. So AX is equal to negative BX. So one of these is assumed the wrong direction. But because I have this member, okay, is putting in, it has x and y components, I'm going to have to be pushing back with an x component here, which means overall AX is going to have value. But my actual equation for this member is AX plus BX equals 0. It is not AX plus BX are all 0. Okay, and if I had assumed one of these in the correct direction, I would have had that they just equal each other without that negative sign. So I've done all that I can with this, and I've got my relationship for later. So now I'm going to go look at free body diagram of BC. Okay, So if I look at BC, I do know that BY is going down because I assumed it the wrong direction, and it's going down at 75 pounds. So I can sum the moments about C equals 0, and I can calculate this X force, which I assume to the left. Okay, so here's C. If this is a clock handle and I'm applying a moment, doink, I have a negative 750 pound-feet. Okay, I have BY. It is going down because I assumed it wrong here, so I switched it. So I have BY coming down. Again, here's my clock handle, doink, rotation. So I have plus 75 pounds. Its vector path lies in this vertical plane. So the perpendicular distance is that X. And if you want to think about it, Fy dx. Okay. And then I have plus Bx times, okay, here's the X. I assumed it to the right, so it's causing clockwise rotation. And it is 3.464 feet. I just look, where is that vertical distance that's perpendicular? But if you want to remember it, that Fx times dy, be my guest, okay? And all of this has to equal 0. So we're trying to isolate Bx. So I have 3.464 times Bx equals a positive 750 minus 75 times 2. And we have 750. Then I have 75 2 times minus. So I end up with 600. And if I divide through 3.464 divided by, I get that Bx equals 173.2 pounds. Okay, and it's positive, so my direction is correct, which makes sense. This is a huge moment right here. 75 times 2 is not very much. I'm going to need Bx also creating that positive moment because this is a huge moment in the other direction. So now that I know Bx is the direction I assumed, I can come back up here, and if Bx is going to the right as correct, then I can see that Ax is actually the negative, so Ax is 173.2 pounds going back to the left. I assumed it wrong. Okay, which makes sense. This moment is trying to take the whole frame to rotate clockwise. If this whole frame is wanting to rotate clockwise, I'm probably going to need a pretty big force here pulling back to keep it in place. And if we're wanting to rotate clockwise, okay, this bottom piece is going to want to joink, also rotate. So we're going to find that Cx is going in this direction, which makes sense, okay? I'm going to have equal and opposite x's, and it makes sense that this is wanting to push that frame leg back. So we're going to continue with this piece, and now that I know Bx was correct at 173.2, I can sum forces in the x direction, and I get a negative 173.2 plus Cx equals 0. So Cx equals 173.2 pounds to the right, like I assumed. Okay, sum forces y equals 0. That By is going down, so I have negative 75 pounds, plus Cy equals 0. So Cy equals 75 pounds going back up. Okay, I hope that makes sense. So if I were designing the shear pin, remember that my reaction at C is actually the magnitude of the pin, of the force on that pin. So it's really, we've got to use Pythagorean theorem. So I have 173.2 squared, 75 squared, plus square rooted, and I get 188.74. And if I just want to do a quick check, Okay, a quick check. If I were looking at this as a 2-force member, I would see that that Y force, okay, would have to be bigger than the X force by our 2-force standard by using the rise run. And what I'm actually noticing is that X force is much bigger than the Y force. It is not, they did not come down to being a function of the 60 degrees because it's not a 2-force member. So you have to make sure you use that sparingly. Okay, thank you.